so there was this weblog, the N-Category Café, and like a week ago something happened, which was one of the most prominent people there decided he's never going to work in N-categories anymore, named John Byers. So was he sort of leaving a sinking ship or something like that? So these guys have to convince us that it's not the case.
Are we meant to talk?
Yeah.
I think as far as John's concerned, I think he just wanted to do something else. I mean, he's been incredibly active in stirring things up for at least 15 years, and I think, well, he wants to go and do stuff on climate change. I don't know. I take that reason at face value.
It won't last. He'll come back. But we've expanded. I mean, we were the three of us, John and myself, and now we're 8. So we're growing.
Right. So is there a future for N-categories? That's what I...
Well, I mean...
Anybody else can ask questions too, of course.
I think... Can I just quickly reply something? I think John has repeatedly said himself something along the following lines, probably better than I will do it now. I hope I'm saying this right. So it seems he said something like, one reason he is quitting is that there's too much going on in N categories these days. He has this feeling that he rather works on topics that are esoteric or at least not mainstream or not even sub-mainstream, something. So it seems that one reason he's quitting is that it's no longer a secret in categories, but it's become real.
Yeah, I think he has said that kind of thing. We're on film, so we've got to be very careful what we say about John. But yeah, he has said that.
So in a sense, it's been too successful.
Yeah, maybe. Yeah. No, Baz was going to ask.
So in Tom's blog post, you mentioned the use of modular type theory as an internal language for N categories or some kind of N categories. How do you do this?
I think you're reading a lot more detail and expertise into those few sentences.
You were not the only one giving hints like this.
Okay. I think you should answer your question.
But I want you to say it.
I don't know what to say. I mean, there's been stuff. I'm just going to embarrass myself here because I don't know anything about type theory, but I've got this vague impression that people. Who is it? So there was Steve Audi and Michael Warren and Peter Lumsdaine and also Benno van den Berg and Richard Garner have been doing stuff on the connections between higher category theory and type theory, and this seemed very interesting to me, and I'm not the person to explain this stuff. I just don't know. Someone else Richard should be here, and then he'd be able to explain it, but he's not, sadly. So
Maybe you should add Kowalski and André Gérard too.
sure. And maybe someone else here wants to explain this. Maybe someone knows.
It's not an easy thing to. I mean, it's not an easy and simple thing to explain, because actually the connections aren't completely straightforward. Depends upon what you're doing with the type thing. And also, at the moment, maybe doesn't capture. I mean, the use of the internal logic aspect of it, I mean, it's perhaps not capturing old dreams. So, I mean, there's an old dream that you sit there with some form of Martin type theory, and as soon as you developed the theory of categories in it, it's clear that categories don't form a two-category in any sense, but a bi-category object, as it were. That the whole of the development of category theory within the type theory is a higher dimension, or something rather essentially Greek-modernist. So there's a lot more to be done, and the internal logic not being used as internal logic at the moment in those sorts of ways. So I think there's
nowadays ridiculous to be interested in n categories without being interested in infinity categories?
Depends how large n is.
Yeah. I think infinity categories have always been an important value of n.
Do you mean in the infinity, comma, n ones?
Yeah,
Where they're invertible above a certain point?
right.
Those ones? No. It's probably aimed at you.
No, I think the way to look at it is as an example of a general phenomenon in math where you have this duality between very simple, very general definitions whose concrete objects satisfying these conditions may be hard to get under control, and very specific objects with very specific properties that you can actually do something with. And I think what's going on is that we see there's a very simple general definition, higher categories. If you first raise the invertible morphisms, if you let them go all the way to infinity, and it's easy to talk about the general structures. It's very easy to say what an infinity group what is. Much easier than to say what an n group what is. It's easy to say what an infinity stack is, all these things. But if you actually want to have a concrete object in your hands, then due to this duality, it may be that even though the general definition was simple, actually getting one object under control may be hard. So for the concrete applications, we want to find in this general context, nice context of possibly very bad objects, you want to find the good objects. Particularly, we want to find strict n categories or n categories at all in the first place. It also has to do with extracting information from these things, right? We know, as implicit said, that as a Kahn complex is sort of the same information as encoded in a nice topological space. So there's a huge amount of information there, all the homotopy groups, all the Whitehead products of this space. But just writing down the conditional Kahn complex is baby stuff, right? You can teach this in kindergarten, but still all this information is encoded there. So now it may happen that you actually need a n groupoid with these and those homotopy groups, with these and those Whitehead products. You want, for your application, because you need to manipulate this, you want very concrete algebraic control over all these data. So then what you want to do is you want to find a model for some n groupoid that is as strict as possible in your context, with as much algebraic control, but still you want to know that under some nerve operation or something, this very concrete algebraic object is an example of these things given by the very simple definition. I think that's what's going on. And I think what for a long time dominated maybe higher category theory was the concrete algebraic models, and maybe what we've seen lately was, I think, what I regard as huge progress in developing the full theory, defining in terms of the very general definitions. And now we can all play around with these things and move back and forth from the abstract definitions to the concrete models. And so no, it's not ridiculous to think about n groupoids. What is ridiculous, I think, is to reason about n groupoids without being aware that there are actually special cases of infinity groupoids. In particular, one sees people doing, forming co-limits or kernels of n groupoid things without doing it the right way, right? So once you know where your objects actually live, that they do live in the infinity category of infinity one category of infinity groupoids, there are good general abstract notions of category theory, limits, co-limits, namely everything in the infinity world, homotopy limits, homotopy co-limits. So, for instance, if you like to study n groups these days, you should continue to do so, but be aware of the fact that working with them is a special case of working with infinity groupoids, which tells you what kind of tools are the right tools to handle these things.
So your answer is yes, really.
No, he said no. He said it's not ridiculous, right? But just be aware.
I can partly guess the answer. What would you see as extra mathematical motivations to study higher category theory? So from physics, surely this is the part I can guess, but what would the others say?
David, just say something.
For me, well, I kind of got into it by accident to some extent. I was just interested in, how does maths work in general. And there was John Byers, who was very conveniently sort of explains stuff in ways that you can understand with a modicum of background. And by chance, it happened to be something that on the face of it, it looked like, you know, if you think back to the big changes in late 19th century maths of a sort of philosophical nature, you'd want to look at the foundations, the logical work, Frege through to Russell, and then also Hilbert and others. And then you could also make an argument that the geometric transformations of the late 19th century were philosophical as well. Although typically, I mean, they're the sort of Riemann, Helmholtz, Poincaré, sort of on the, you know, they all knew their Kant pretty well, these people. So yeah, they're kind of two things. I suppose it was wonderful then that the example that John Bowers led me into involved both these issues. I mean, as we were saying, you know, there's the geometric side and the logical side when you're dealing with toplesses, for example. So that, you know, that was even better. We've got both kind of aspects of philosophical interest at play here. I mean, there's a big question for me. Why should a philosopher be any use of developing this theory rather than anybody else? I mean, it seems there's no good reason why that should be the case. So I sort of come along for the ride. I just enjoy, you know, watching these guys work.
May I try to reply to the question? So the question was, if I understood correctly, what's a purely mathematical motivation for high category theory?
No, what's an extra mathematical?
Extra.
So what is not purely mathematical motivation to do so?
Not. Ooh, okay.
Well, it's physics.
We did the physics. I'll say what I wanted to say anyway, maybe. So one huge motivation, so geometry is motivation, right? We want to understand geometry. This is what we try to do for hundreds of years, I think. So much of the new development of high category theory comes, that's why these things are titled this way, comes from generalizations of algebraic geometry. So what's happening, people are finding examples of generalized spaces that are not plane spaces. As far as I can tell, so much of this development originates in the Gers-Hopkins-Miller theorem, who observed that there's this thing called the moduli stack of derived elliptic curves, and they noticed you can associate to each elliptic curve a spectrum, an E-infinity ring, something that's like a ring but infinitely categorified. And well, that was known, that's cohomology theory, but they observed that you can assign these rings to the points of this moduli stack in this collection of all elliptic curves in such a way that they seem to glue together in the correct way. So the structure, this moduli stack of elliptic curves, looks as if it has not just a sheaf of sets of functions, but actually an infinity stack of infinity glucoids of infinity functions. That's just something one observes. That's a theorem they've proven. And my impression is that much of the development comes now from looking at this example and saying, okay, so what would this actually mean? That we have all these infinity rings assigned to all these points. So you said, okay, it should apparently be true that this thing, this moduli stack, is actually an infinity space, an infinity scheme that has infinity functions on it. So you start, okay, so to make sense of this, we need to know what's infinity category theory, what's infinity sheaf theory, what's infinity topos theory. Then you want to know inside there, what are spaces in there, infinity ring spaces, infinity locally ring spaces, infinity schemes. Then you want to know, okay, so they will have some function rings, infinite rings or simplicial rings, so you start continuing this way. So you need to understand infinity algebra, infinity commutative algebra, infinity deformation theory. So all these, geometry leads to lots of math. So one goal is understand this higher geometry that you see appearing there, and I think one very nice message is here that lots of math, lots of higher category theory is about higher categorical generalized spaces, namely about higher topos theory, which is a very, I think, for category theory, it's a very nice message. Higher topos theory plays a role.
Where can we find out more about higher topos theory?
Could you say this?
Where can we find out more about higher topos theory?
Where? Where?
or in Lurie's book.
Yours.
How many pages?
And so one should actually, so much of, I mean this, so there's also, for instance, so there's some predecessors to this book which maybe worthwhile looking at. So there's a series of articles by Bertrand Touraine, and I hope I pronounced the name correctly, Gabriele Bezzosi, and also by Charles Resk, who, as far as I can understand, actually was the originator of the idea of an infinite topos. Here on his website is a nice set of lecture notes downloadable as a PDF called Model Topos Theory or something. That's Resk. There's Lurie with his big book. There is Touraine and his co-author Bezzosi.
Don't forget, don't be modest, don't forget the NLab. Urs explains lots of this stuff online, you know, on the NLab.
Well, when you
But then
so
not-
as soon as you Google for this, you will see NLab links coming up.
I've got a question. Can you explain the NLab? I think some other people maybe want to hear what this is.
Should I ask the other
Well,
one?
you,
Yeah.
you do most of the writing.
I don't know, maybe I don't know what the NLab is. Maybe it's very different things to different people. so it's a.
Urs has got shy, I'm going to explain. So it's a place where there's lots of fantastic maths explained, and it's a wiki, and I think Urs views it, correct me if I'm wrong, as a place where you write down stuff because you want to, for selfish reasons, right? But it has the side effect that other people can go and read it, so it's a good resource for the rest of the world. But somehow it's one of these things where if you decide you're going to be altruistic, then it becomes a burden, but if you decide you're acting selfishly, it becomes a joy. Yeah, so there's lots of great stuff there. But I mean, it's picked up a lot by Google now. So if you search for something as some mathematical term, then quite a high proportion of the time it comes up with an NLab link if it's something categorical. So yeah, and anyone can edit it. Or do you have to
Everybody is actually invited to edit it. So maybe to what you said, I add the perspective that it's called a wiki, so it's a collection of internet pages in which have the intent to present aspects of math, new math, old math, from what we started calling the N POV, the N point of view. So Wikipedia has this, they have the rule that everything appearing on Wikipedia has to adopt to what they call the neutral point of view. You're not allowed to go to Wikipedia and say, oh, what all these people wrote here is garbage, I know this stuff much better, so here's how I perceive it. You're not supposed to do this. Everything on Wikipedia is sort of consensus, the lowest common denominator. So on the NLab, the idea is the other way around. We say, no, there's one right point of view, it's the n-categorical point of view. That's the way, the language in which math is written. So, you know, we don't adopt the neutral point of view, we adopt the right point of view. So on the NLab you will find, that's the way it's developing. You will find many things that are a bit like Wikipedia. There are also people doing stuff very different from Wikipedia, but there are lots of just terms explained. Category, Hilbert space, but you will tend to find them described in a possibly non-traditional way on the end point of view.
Yeah, and you can go along and just leave a question. You don't have to give a positive contribution. Well, it is a positive contribution. You can say, I didn't quite understand that. Or,
Yeah, in fact, that's so we do have a handful of regular contributors. The number is slowly growing. I think there's a nice community developing there. Everybody is invited to contribute. Have a look around and see what happens to you.
Just to bring the discussion back to the general level, where would you see the main developments within N category right now? When there's so much activity, it's a bit hard from the outside to say, okay, this is important, this is where the field is going. So where would you see the main lines of development?
I feel like I'm, in some sense, retired, so I'm not going to answer.
You're a bit too young for that.
So maybe the first answer is lots of things are going on here, right? The question is a bit like at the beginning of category theory. Now, so we know now what category theory should be. So what's the most important development now, right? So there would be lots and lots of things. There would be topics. So I think one important development that one sees going on is that we see more and more models of higher n infinity, n categories and their interrelation. For instance, there's a very, I think, interesting model by, again, Charles Resk about what we call theta spaces, which is a refinement of the old idea by Jayal to have free sheaves on the theta n categories, and there are good indications that these theta spaces model infinity, n categories in a very useful way for all n actually. There's just recently that big book by Simpson where a slight variant of such a construction is studied in much detail. So I think what's happening is that now with a good foundation of infinity, 1 category available, which allows you to do category theory also with all these other higher category theories, it's now really possible to do constructive work in proposing and comparing definitions of higher categories. But maybe the most important, well, that's sort of the purely category theoretic aspect. I think sort of the main impetus of the whole thing comes from applying these things. So quantum field theory to derived algebraic geometry, that's the two big, I think, applications for this stuff. And in derived algebraic geometry, there are lots and lots of very beautiful constructions now. Suddenly people, like Plug has been released, you can do all the things that you ever dreamed of as doing, and they work, they exist. Lots of interesting stuff.
What's the derived algebraic geometry? Is that I just read a paper from Rosenberg back in the 90s on non-commutative schemes. Is that non-commutative or no? It's higher category stuff.
So in principle, derived algebraic geometry could, in principle, I mean, there's some differences of what exactly people understand under the term, and of course everything you can do over commutative objects you can eventually try to do over non-commutative objects. The basic idea of derived algebraic geometry is that you say, you take ordinary algebraic geometry, which is about generalized spaces modeled as sheaves, set-valued functors on the category of commutative rings of, well, functors on commutative rings, so pre-sheaves on commutative rings of. So you have this thing, and you know, okay, that's these things model generalized algebraic spaces, schemes, algebraic spaces, algebraic stacks. And you say, for reasons I mentioned, this needs to be categorified. So when you have this functor going from this category to the category of sets here, you can categorify two directions and two ends of this functor. First thing is you can say, okay, this actually sends a commutative ring no longer to just a set, but to an infinity, one group point, two group point, and an infinity group point. And you say you have 1 stacks, 2 stacks, infinity stacks, algebraic infinity stacks, like Deligne-Mumford stacks, Artin stacks, higher versions of these. And if you look at what's happening there, effectively what you're doing, you're describing orbifold-like structures. So you can think of the categorification here as taking care of quotients of your spaces. You want to be able to say, okay, if a space in which some group acts, and I want to be careful about quotienting out this action. I don't want to do it on the nose in the naive way, but up to higher categorical cells. I can accomplish this by passing from schemes to stacks, higher stacks. But then you notice, oh, that's still sort of not good enough. if I look at intersections of these generalized spaces, they still misbehave. They don't interact well with the cohomology first. But also it's no surprise you've infinity categorified this functor just on one end. So what you want to do, you want to also say, we also replace the category of commutative rings of affine schemes with something higher categorical. So what you do is, you say, oh, let's look at spaces that don't have just, we mentioned this before, that don't just have a ring of functions, sort of a homological resolution of a ring of functions, that have a simplicial ring of functions. That's one thing you can do. You can take an infinity ring of functions, or in fact there are many possibilities. But let's stick to this algebraic motivation that what people are currently looking at. And you say, okay, here's an infinity category of infinity rings of infinity affine schemes, and on this we have an infinity stack with various infinity groupoids. And derived algebraic geometry is about these things are then called derived stacks. In a way, because your domain category, you've derived the domain category. You passed from an ordinary category to something like its derived category in the correct sense. So that's what derived algebraic geometry is about.
Okay, but no, because Kohn made that big step with non-commutative geometry using mainly functional analysis. And of course, algebraic geometers and category theorists, is there now a non-commutative scheme theory?
I mean, the concepts of derived and non-commutative are orthogonal. So you have derived, commutative, derived, non-commutative, non-derived, commutative, non-derived, non-commutative.
Oh, okay. Which is sad.
No. I'm saying you can do either or both or neither.
But both is perhaps possible.
Certainly, this is a really hardcore thing. I mean, you just mentioned that, right?
Because that's the big thing. I mean, Kohn made that step, and that's one paper I read. But it's obviously it was from MPI in Bonn, Germany, with Gerd Faltings, and but there doesn't seem any, and it's readable for me. I mean, I'm a beginner, so, but there seems to be no further development. But if you say so, in that higher dimensions, perhaps there's a way.
So here's a nice way to think about this. In the development of non-commutative algebraic geometry or non-commutative geometry is specifically done by Maxim Kontsevich. These non-commutative spaces are all conceived in terms of their A-infinity categories of quasi-coherent sheaves. You encode everything, all these non-commutative things, in terms of, well, the corresponding sort of abelian sheaves, quasi-coherent sheaves over them, which form an A-infinity category. So here's one of the very nice results of categorical results of this new category theory. These things called A-infinity categories or DG categories that people have studied for such a long time actually do have a nice, entirely abstract category theoretic interpretation. Namely, they're precisely models for what's called stable infinity categories. So the infinity version of an abelian category. There's a one-line, very nice intrinsic definition of what it means for an infinity category to be abelian in the right sense. And it turns out that what people used to call DG categories or infinity categories are precisely models for these sort of incarnations of these abelian infinity categories. And then there's the following nice relation which might help to put commutative derived geometry with the non-commutative version in perspective. So we know we can think of a petit topos as a generalized space of sheaves on some space, where sheaves is notably not abelian sheaves, but set-valued sheaves. So we've seen how you can generalize this to an infinity topos, where you think of the petit infinity topos as being the infinity stacks, the infinity groupoid valued infinity sheaves on your would-be space. You characterize your space by looking at what sort of the non-abelian functions, infinity functions on it are. Now, there's a way to stabilize any infinity category. You can take this infinity topos, infinity sheaves on your space that characterize the space, and force it to become abelian in a sensible way. And the result will, by definition, always be a stable infinity category, so particularly correspond to some A-infinity category. So you can think of this as taking here your space, you characterize it by its kind of strange. You characterize it by non-abelian functions in a way, infinity groupoid valued sheaves. You can abelianize this It's funny, right? But that's the way it works. So, and look at just infinity B and G quasi-Fourier sheaves on it. You find an A infinity category. It's no longer a generalized space in the sense of topos theory, but a generalized space in the sense of generalized non-commutative geometry.
It sounds like cohomology then. If you have a sort of quasi-abelian thing, you might be able to do cohomology, right? No.
Well, certainly cohomology is an important concept here, yeah?
Yeah. I think we are
Coffee.
The coffee.
Yeah.
So the thing is, to get to the coffee,